Assalamu alaikum and welcome back. Up till now in this course, we have exclusively focused on the scientific method of doing network performance evaluation studies. This may give the wrong impression that network performance evaluation is only about the scientific method in which we have almost a mechanical way of giving some parameters and getting the results as an output. But we would see, and that's the focus of today's session, that network performance evaluation studies is a lot about judgment and intuition. Specifically, we'd be covering the art of modeling today. The reason we need models is that often in practical terms it is difficult to perform evaluation on actual systems. So this may be because the actual system does not exist yet. For example, if you're doing design of a system that you're going to build, the system does not exist yet. In other scenarios, you may have a system disrupting which is impractical. So in those cases as well, instead of doing studies on the real system, we make a model of the system and then we perform evaluation on that. However, the element of judgment comes in the aspect of modeling, because there is no single universal model of a system. And different modelers may come up with differing views of the same thing, because when we are doing modeling, we are abstracting the system, which means we are taking away some of the details and presenting a more simplified version of the system. So because of that, the version of the system may be different in the eyes of different modelers. So we may have different models. So we'd be covering aspects of modeling today, introducing what modeling is, what kinds of models are used in network performance evaluation, and lastly, but very importantly, we'd be covering limitations of models. So we'd be seeing that models are always approximations and they are not the reality. So we should not extrapolate our results to the level of certainty that we start believing that our model is the actual reality. So we start with an introduction to modeling. So the first question we must ask ourselves is, what is a model? And we define a model as a purposeful abstraction of a system. So this is important, the usage of the word purposeful, because the abstraction that we are doing, where abstraction simply means removing some details, is actually a function of the task that we are going to perform. So for different tasks, we are going to have different models. And we use models all the time, but we have different sorts of models, and we'll be covering specifically the types of models that exist. So initially, we can talk of the example of a map. A map is a model of some land or some space. And we have different examples of maps, because maps may have differing amounts of details. So depending on the purpose of creation of the map, you would put in the amount of detail there. So that is very important. If you are just interested in seeing, as can be seen in this slide, how different buildings are located in a university, you are not really interested in depicting the topology of the land, the relative elevation of the land, or the vegetation on the ground, or even the kinds of roads you have. All that you are interested in is the relative positions of the buildings. But you may also be interested in knowing about the topology if your work is related to that. Imagine that you are working for a company which is going to install certain equipment in this area. Then you need to know the relative positions of the poles, the electrical utility poles in this area. So a map in which the poles are not shown would be useless for you. A map in which the poles are shown would be very useful for you, even if the other details are missing. So this brings us to the same important point that I've earlier made, that the model that you actually use is actually tailor-built for the purpose that you're trying to solve. So there is no universal model. And the important point here is, then how much detail should we have in a model? So it depends on the kind of model you're using. If you are thinking of a physical model, you can imagine, for example, the toys that children use. So they would have replicas, small replicas of big cars. In such a case, you want to have as much of the physical details as possible so as to make it more realistic. But in terms of network performance evaluation studies, often our interest is not in including the detail. Our interest is more in excluding the detail, as long as the essence of the concept that you are trying to capture is actually captured by the model. So this is illustrated in a principle stated by Dijkstra, who's also famous for his Dijkstra algorithm for calculating the shortest path tree. He says that remove what can be removed. So this is actually very good advice, not only for modeling, but also for all aspects of communication, writing, speaking, presenting. The general design guideline here is that remove all the extraneous items. Everything that is not pertinent to your task or the thing that you're modeling for should be removed. So we are actually trying to capture the essential core of the reality that you're trying to capture. Another important quote that is relevant here is made by Einstein, who said that make things as simple as possible, but not simpler, because you want to capture the reality and capture it in as simple a way as possible, but it may be that if you make it more simple, you're going to lose aspects of the reality that you're trying to model. So this actually conveys the idea of abstraction, and we see that the aim of a network performance evaluation modeler is to remove as much detail as is possible without compromising on the thing, on capturing the thing being modeled. So to illustrate the idea that all models are wrong, but we use it still because they're useful, let's talk of an old story. So you might have heard of the story of 6 blind men and the elephant. So these 6 blind men actually came upon an elephant, and they started inspecting different parts of the elephant and started forming different mental models of what they're actually evaluating. So the first person, the first blind person came up with the trunk of the elephant, and he thought that this is a snake because it moves. So that is how he captured the elephant, the reality, in a model. The other person came upon the tusk of the elephant, and he thought that this is a spear. Another person touched the leg of the elephant and thought that this looks like a tree trunk, so this must be a tree trunk. Another person, touched the body of the elephant, and he thought that this is a wall. Another person, he tried touching the tail of the elephant, and it looked like a rope to him. So 6 different people have 6 different impressions of the same reality. So they have differing versions of what the reality looks like. And that is the truth of modeling as well. In many cases, we do not know the real reality. And what we're trying to do is make a best estimate. So in certain cases, we'll be seeing that it is actually useful to make many models of the same system, because having multiple models, it gives you more information about the reality of the system, because no single model is going to capture the entire reality. So it is said that no model of a system is exact. Only a duplicate of the real system would be an exact model. So our aim in modeling is not exact replication of the system. A quote by George Box, a very famous statistician, is in place here, and this is a very famous quote. He said that all models are wrong, some are useful. And this is the essence of modeling. We do not throw away the concept of modeling just because they are approximate. This act of approximation actually helps us. The reason is that it's very hard to comprehend entire reality. It's very hard to analyze the entire reality. But if we can capture an approximation of the reality and analyze that, we get to know something about the system. We can also form a model and do some prediction on the basis of that. So The idea here is that the aim of a model is not to be exact. Its aim is to be useful. And we define useful in terms of the context of the subject that you are trying to model. So we can think of this in terms of sampling. So we've already seen that in many cases, we are actually estimating about general characteristics of a population on the basis of a sample. But what philosophical justification do we have for this? We already know that a sample will never exactly represent what the population is. So we already know that this is an approximation. What is the benefit that we are getting out of it? The benefit is that, it is convenient for us. We are not going to go and check every member of the population. We're just going to get a sample, and based on that, we can extrapolate judgment about the entire population. And furthermore, if we are assuming random sampling, we can actually put an estimate of the amount of error that we'd be having. Let us now study why do we actually need models and where are models applied. So we've already mentioned that modeling is used because it is often disruptive to an actual system to conduct performance evaluation study on it. In many cases, for questions of design, we may also not have a prototype. The question that where are models actually being used? So the answer is practically everywhere. So every field of interest that is of any practical importance is using models. So it is used in the context of analysis. So analysis means that you want to analyze the current status of your whatever subject that you are studying, and you want to make some predictions. So an important area in which we're using predictions is the field of finance. So we make use of mathematical models to predict, but unfortunately these models are not very accurate all of the time. So an example can be seen in the slide here. So you see a graph of actual thing being measured, and you also have lighter lines which are showing projections of estimates of this. And we always see that the estimate is a little off the actual mark. And this is because often it is very hard to make predictions about the future. And financial market is notoriously hard to model. But the thing that I'm trying to convey here, that even the financial market is making use of mathematical models. And we'd be showing in the end of this session that mathematical models is not a panacea. It is not magic. So if you rely too much on mathematical models, you're actually going to face a problem. And this is actually illustrated in this graph. You can see that the 2008 credit crunch problem was actually created by too much dependence on mathematical models without understanding the real reason or the real assumptions behind those models. We can also use models for understanding systems, because it is very hard to get our hands around reality because the system may be very complex. But if we simplify the reality and make a simpler model, then we can tweak the model and see how the model responds in response to certain input changes. So you can answer many what-if questions. And when you're doing that, you're learning a lot about the system. We can also use this for testing and design. And we often use computer simulation models for this, because it is often the case that in the design phase, the prototype does not exist. What you can do is you can build a model in computer, some programming language can be used to actually build a model in as much detail as you want. And then you can test the model for various input conditions. And then you can make predictions on the basis of that. You can also make design choices and compare design choices on the basis of such models. So one thing I would like to stress again is that there is no universal model for a system. If the same system is given to two designers or two modelers, chances are that they would come up with a similar model, but which would be different, because you can model the same reality in different ways by making different assumptions. So to illustrate this and to show how the scientific process actually progresses, I'll take an example from history. So we now know that the sun is at the center of our solar system and all the planets revolve around this. But for around 1500 years, people actually believed that Earth is at the center of the entire planetary system, and even the sun revolves around the Earth. So these are both models, and the idea is that you can always interpret the data in terms of the model that you have. So the people who believed in the geocentric view, the geocentric view is where the Earth is at the center. They thought that the rising up of the sun and the setting of the sun is actually testament to the fact that it is sun which is actually moving. But it was then proposed by Copernicus that it is actually, we have a heliocentric system in which the sun is at the center. So now I'd be conveying what different models can actually exist. To understand this, we'd be seeing how Copernicus system was actually shown to be true and improved upon by Kepler. So Johannes Kepler was actually someone who worked at the observatory of Tycho Brahe. And Tycho Brahe was a person who had kept very meticulous observation, the best observations of his time. And based on the data he had, Kepler fitted a model to the data. He did not really understand the reason for arriving at the conclusion, but he discovered through the model of curve fitting, or essentially forming a regression model, he discovered that actually the planets do not revolve in a circular motion. In fact, they move in the form of ellipses. But he did not have a physical explanation of that. But still, this actually improved the model of both Ptolemy and also Copernicus, who both thought that planets move in circular orbits. So this is an improvement, but this is not an improvement which actually gives a lot of insight of how actually the planets are moving in ellipses. But because the results of the data and the hypothesis that planets move in ellipses were so close, it was believed that planets actually move in ellipses. And this thing was shown to be a physical law and a consequence of the gravitational law by Newton. So first what we had was a simple statistical model of how things are working. So Kepler saw the data and said that it does not look like the planets are actually moving in circles. He proposed a statistical model, and we later on discovered the physical reality of the inverse square law gravitational force, which was proposed by Newton, which explained why planets move in ellipses. So the idea I'm trying to convey here is that you may have different models for the same reality, and they may actually be matching data both. In the case of the Copernican system and the system proposed by Ptolemy, both of them were actually similar in terms of how they responded with observations. Even the system proposed by Copernicus had some errors, but that error was due to the fact that Copernicus believed that the planetary motion is in the form of circles. This was improved by Kepler, and the physical reality of this was discovered by Newton. So science is a process of making iterative models, of successively improving your models. And we can always have different models for the same reality. And we know already that all models are wrong in the sense that they do not capture the exact reality. Even Newton's law is now shown to be defective in certain cases by the theories presented by Einstein. But we will not be going into that. We'll suffice by stating again that multiple models can exist for the same process. If multiple models can exist for the same system, how do we then differentiate between a good model and a model which is not very good? So the basis of this distinction is actually governed, or it is given direction by what is known as Occam's razor, which is a principle which states that if there are multiple competing hypotheses trying to explain the same reality, we accept the hypothesis which makes the least assumptions. So we choose the simpler hypothesis. So this is actually, gives a guideline of how to build models. So we would actually be always striving to build parsimonious models, where parsimony is a term which defines how stingy is a model in terms of its parameters. If a model requires too many parameters, we would say that this model is not parsimonious. And we strive to achieve parsimony in our models. An example is that if you want to study the air resistance of a car, for studying that you do not need to know a lot of the internals of a car, but the shape of a car is important for your concerns. So if you have a model which is showing the shape of the car, that is sufficient for your needs. And we can shave off all the extraneous details as suggested by the principle of Occam's razor, and we arrive at a model which is parsimonious, or which makes very few assumptions, and it is lean. Lean means it does not have too many assumptions. So on the other hand, if you have a model which requires too many parameters, you have what is known as the problem of overfitting. So it is actually observed that if your model has too many parameters, it can practically match all possible data sets. So if you have only 2 data points, you can always form a line through it. If you have higher number of points, you can find, if you have enough parameters, you can always form a model which exactly describes the data that you have. But then if you have an overfitted model, it then only can describe the data that you already have. It does not really give you any intuition about the general characteristics of the system being modeled. In other words, on the basis of this model, you cannot predict anything in the future. While your model would be matching everything that has come in the past, it will not be able to predict anything in the future. We've already talked of simple linear regression in earlier sessions, and in simple linear regression, a dependent variable is assumed to be dependent on just a single independent variable. If we extend this concept, we have what is known as multiple regression. And when we are doing multiple regression, for any given data set, you can always form a model, assuming that you have enough parameters to exactly describe the system. But if you choose too many parameters in your multiple regression, or too many variables, and you're choosing their coefficients arbitrarily, then this model actually loses all the ability to predict future occurrences. So this would not be a very good model. And there's a very famous quote by von Neumann towards this end. He talks of the problem of overfitting, and he said that with 4 parameters, I can fit an elephant, and with 5, I can make him wiggle his trunk. So the idea is that even if you have a very funny looking data set, if you have enough number of parameters, you can always have a very close match between the model and the data set. But that should not really impress us, because this is a given fact that with enough parameters, you can always have an exact match with data. The problem is that this model would invariably be very bad at predicting future occurrences of data. Let's now talk about the different kinds of model that exist. The first model that I'd be talking about is a conceptual model. A conceptual model is a cognitive model in your mind which helps you understand things. In many cases, we can often form a model of a very complex task in the form of a flow chart. So this would also be a conceptual model. And a conceptual model which would be very familiar is the OSI model, or the TCP/IP model, in which the entire task of communicating across a network is broken down into various layers. And the layers actually interact amongst amongst themselves. And we can also imagine peering layers that they are talking amongst themselves. So there is two levels of abstraction. One is that the top layer is actually talking with the underlying layer in the same machine, and with the communicating machine at the other end, you can think of yourself as talking to the peer layer at the other machine. So this is shown in the slide here, and we see that you can imagine a user of an application program would be thinking that his process is communicating with the process at the other end. So a person who starts up a browser, he can think that his browser is actually connected to the web server through some logical channel, and he abstracts away all the underlying details. But this is a model, this is an approximation. This is not the complete reality, because any socket programmer will let you know that application layer processes cannot talk between themselves without forming sockets, and it is actually the sockets that are communicating. So then, is the model of socket layer to layer communication, is this a complete model? This is again incomplete, because sockets are not connected in vacuum. They have to be transmitted in terms of packets. They have to be transmitted over physical channels, and eventually this thing has to arrive at the destination network, to the destination host, and is then delivered to the destination process. So the entire reality is quite complex, but you can always break it down to understand using a conceptual model. So in addition to conceptual models, we also have what are known as physical or mechanical models. They are also known as iconic models, because you can always replicate some device of a bigger size by a smaller size device. For example, the example of a globe. So it is a replica, a model of the Earth. It even has on it the continents and the amount of water there is and the amount of land there is. But at the same time, it's just a model. It can tell you some things about the system we are trying to model, but not everything. The models we'd be interested when we are doing network performance evaluation study, these are mathematical models. In a mathematical model, we abstract the system in terms of mathematical symbols that are manipulated, and we can express them in the form of computer programs or in terms of equations, in terms of mathematical equalities or inequalities. So these are all examples of mathematical models. Furthermore, these mathematical models can be divided into many subtypes. So you can see a list on the slide now. The first kind which we have listed is a differential or a difference equation. So if you've studied signals and systems, you would know that the input to a system and the output to a system can always be modeled by a differential or a difference equation, which is characterizing the transformation the system does to the signals. You can also talk in terms of statistical models, and we've earlier talked of statistical models. In statistical models, the relationship between an input and an output is a statistical one, in which we can state average characteristics, but we cannot state what will happen every time. So you have a probability distribution of how the output can look, but you do not know deterministically of what the output would be. You can also have a deterministic model, and in that the exact output can be predicted knowing the input. A statistical model is often known by the alternative name of a probabilistic model. So there is some similarity there. And furthermore, the models that we use most in network performance evaluation studies are the analytical models and the simulation models. In an analytical model, you are expressing the relationship between the input and output by an analytical relationship. So this may be using some mathematical formalism. For example, you may think of a probabilistic model or using some other mathematical technique, but you express that in terms of an analytical function. So it may be a single equation, it may be a lot of equations in which you may have a closed form solution, or you may have a numerical solution in which you iteratively solve the equations. But the analytical models are often the simplest models, because if something can be modeled by an analytical model, the model can be solved very quickly. But the downside to this is that it is, very few models which can be approximated by an analytical model, because they make many simplifying assumptions. So if you want to make a more realistic model, we often have to recourse to simulation models. In computer systems, we can always build a simulation model using some programming language in which we can go to any level of abstraction. So we can make a simple system, or we can make as complex a system as we want, subject to availability of time. So because you need programmers to actually program the code for the simulation, and then running the simulation often takes a lot of time as well. You have other sorts of mathematical models like game theoretic models, in which you are modeling the decision between two different entities. How do they interact amongst themselves? You can also abstract a system in terms of a graph, in which various systems are represented by nodes and their connections by links. But we will mostly be focusing on analytical, statistical, and simulation models. So let's first talk about analytical models. In an analytical model, we try to see if the system we're trying to model, if it can be represented by an analytical function. Often we take use of queuing theory formulas. So queuing theory is a very developed field in which the general idea is that you have a server and the clients are coming. The server is shared amongst multiple clients. So when multiple clients come at the same time for service, they would line up in a queue, and as soon as the current customer which is being serviced, or the current client being serviced, is serviced, the next client can actually go and get service. So many practical systems can be modeled using a queuing system model. So we actually have an example here. Imagine that we are interested in finding out how much buffer space do we require at a router for a given incoming pattern of packets. So we are given what is the inter-arrival time of packets, and we want to know that what is the buffer space that we would require. So for such systems, if we are willing to make some simplifying assumptions, like the service time is a very simple function, उसको आमतौर पे हम एक simple distribution से represent कर सकते हैं. The simplest possible distribution here is the exponential distribution. इसी तरह हम ये भी assume अक्सर करते हैं कि जो input आ रही है वो एक Poisson process है, जिसमें inter arrival time जो है वो भी एक exponential process है. This is actually just an assumption. We must not confuse our assumption with properties of the real data, because real packets, they are often not memoryless. वो जब एक साथ ही आते हैं, they come in bursts, and your service time is actually also dependent on the size of the packets. But let's assume that we just want to approximate. We do not want a very realistic estimate. In that case, we can model this as a simple kind of a queue, and from that we can get a result which you can see in the slide now, that we have a relationship between the utilization of the server and the number of items that we have in the queue. So we can see that if your utilization is near zero, you have almost no customer in the queue. Every time a customer comes, he immediately gets service. On the other hand, if you have a utilization of almost 1, you have infinitely increasing number of customers in the queue. So this is just a simple formula, and it gives us a lot of insight into the system. But the idea is that the real system may not be, approximated well by the assumption that we are making. So we should always remember this. And a very insightful comment which I've come across by an author known as Havercott, He said that analytical modeling is the process of finding that 10% of the system which explains the 90% of the behavior that you're interested in. Analytical modeling में अक्सर हम बहुत सारी simplifying assumptions लेते हैं. But if our simplifying assumption is consistent with the task that we want to do, हो सकता है कि हमारा मॉडल रियलिस्टिक नहीं है, लेकिन जिस पर्पस के लिए हम इस्तेमाल करना चाह रहे हैं, if it is consistent with that, then we can use this model. Okay, let's now talk about statistical models. And I talk about statistical models in two varieties. The first one is the univariate model. Isme, it's important to stress that we can think of mathematical ideal abstractions, and we can talk of realistic, versions of things that you find actually in the real world. And we must be always careful that we do not confuse these for each other. As an example, so let's take an example of rolling a die. So if we roll a die 30 times, there are 6 faces on the die. So 1, 2, 3, 4, 5, 6 is written on this die. Depending on what face is facing upwards, we'd be saying that this is the outcome. So if assuming that all the faces are equally likely, agar hum uniform distribution assume kare, so you would have a probability distribution which is shown on the slide here. So you observe that the probability of all the outcomes is equally likely, and you expect that each outcome would come 5 out of 30 times. Imagine that you actually rolled this die 30 times and you observed what actually came out. So it is, very probable that you would actually not get exactly this, but you would get something close to this. So that is the general idea कि जो आप ideal model आपको predict कर रहा है, it's not जो expectation है of a random process, it does not mean that this will exactly happen. But we must remember that this is an approximation. जिस तरह आप अभी स्लाइड पे देखें, empirical जो observations हमने किए हैं, it's almost like the ideal distribution, but still not quite. Just to emphasize this point, imagine अगर हम 30 times की जगह 10 times हम इस die को roll कर रहे हैं, तो your ideal model would predict कि the outcomes of 1, 2, 3, 4, 5, 6 are going to come 1.667 times each. And this is clearly not going to happen practically, because you are either going to have 1 as an outcome or 2 as an outcome. You cannot have 1.667 as an outcome. So this underscores my point that mathematical distributions are ideal distributions, and they actually tell us that what will happen if we conduct this experiment many times. So the actual thing that you observe may or may not observe what is predicted by the model. So similar idea extends to the normal distribution. Normal distribution भी एक theoretical distribution है. It is expressed by a formula, and the general idea is that the central point is the most likely point. The points away from the center can happen, but the happening of these points is very rare. Actual processes are approximations of the normal distribution. You would never have an exact normal distribution, because normal distribution is a theoretical idea. But what you can have is a good match to the normal distribution, or a match which is not very good. In both cases, we have to inspect and see if we can actually assume that you have normal data, and because many parametric statistical techniques depend on this assumption, so it's important that we evaluate if the assumptions that we are making actually correspond to the reality on ground. Statistical models, they also come in the flavor of bivariate models. In this, you are comparing two variables. So this may be a correlation measure or a regression line formation. You also can compare multivariates. So we've given an example of multiple regression. This is an example of a statistical model in which we are forming a relationship between multiple variables. Let's now talk about the models that we use for network performance evaluation studies. And we've covered this in an earlier lecture. So there are essentially three models, and these are analytical models, simulation models, and empirical models. In empirical models, we make actual measurements on systems, and then we form a model from that. It may be that you only have a sample, and then you are trying to estimate about general characteristics of the system. So what we have is an empirical model. If you are using some applied probability tool like queuing theory, you would often have an analytical model. If you're using a computer program to model the system, you often have a simulation model. So I refer you to the earlier lecture in which we discussed and compared these different models, and we gave merits and demerits of each. And we said that we should not always focus on just one technique and apply it to all cases. So there is a quote which I find relevant here. It is said that when you have a good hammer, everything looks like a nail. So what that means is that when you know one tool very well, then you start to apply that everywhere. This may not be appropriate. So as an example, someone who is good in simulation may always try to use simulation. This may not be appropriate when you're studying a very simple system, and you can use a queuing system formula for solving that exactly in a few minutes. So in such a case, performing a simulation is a waste of time. In many cases, you would have other permutations. You want to use one model, but this is not appropriate. So you should always study what tool and what model is appropriate for the task at hand. So we have now introduced modeling in much detail. So let's now talk about some limitations of mathematical models. It's very important to realize that mathematics is not magic. It's not going to give you exact predictions about the future. So whenever you have outcome or output from a mathematical model, we must take it with a grain of salt and realize that while getting these results and getting these exact numbers, we made a lot of approximations on the way, which may or may not be true. So we must understand the data that we have in the light of all the assumptions that we made. So firstly, to illustrate the false confidence that many people have in numbers and in statistical models, let us have a look at 4 data sets. So 4 data sets are shown on the slide now, and these are set A, set B, set C, and set D. And you have a bivariate relationship in each of these sets. And assume that we are given this data and we are asked to find what is the pattern inside each data set, and are the data sets similar in some aspect. So the standard way of doing this is to give all this data to our standard statistical tools to get some measures or to get some statistics and to get some statistical models. So if we do that, we actually come up with some important results. So we see that the mean and variance of X in each case is 9 and 10. We also see that the mean and variance of Y in each case is 7.5 and 3.75. The correlation in the linear regression line in each of the 4 cases is identical. But if you look back at the data, you would see that the data does not seem identical. However, the statistical model, because we can imagine a summary statistic to be a model as well, because it is conveying the whole idea of the data to you in just one summary. So if we see these summary statistics, we would conclude that these data are exactly the same or very similar. So we would be very happy that we've made some discovery then. But if you plot this data, you would see that these 4 data sets are actually quite different. So if you observe, set A is what you would expect, because if we are making a regression line, we would assume that most of the points are close to it, but they do not fall exactly on it. So you have some residuals. Set B looks like a non-linear function. So while we fitted a linear line a line to it, but it looks like we have a quadratic relationship or a nonlinear relationship. So this then shows us that set A and set B are, dissimilar. They are not the same. And for set C and set D, we actually see the impact of an outlier. For set C, we see that most of the data is actually on a line, but the fact that we have an outlier is lowering down the correlation measure. For set D, we see that the data actually does not have a linear relationship, but just the presence of a point at the top right corner, it is creating a sense that these data are correlated. And we also have a regression line which is identical in all four cases. So with this example, which is due to Anscombe, who is a famous statistician who proposed these four data sets as an example of how statistical formulas, simple reliance on that may lack. And this is also motivation of focusing on graphical methods, because graphical methods can show us patterns which do not come out in simple statistical numbers. So with this, I wanted to emphasize that statistical models are not perfect. They may or may not capture the entire reality that you want to model. So in many cases, the results of such statistical models is a good approximation. But we must always understand that these numbers are not going to capture the entirety of the pattern in the data, and we must explore other options. So if we have a statistical model, also explore the option of graphing this data. So I hope this point of not being too confident in statistical model is clear. Let's now talk about some don'ts of mathematical modeling. And this is due to an engineer, Golomb, who actually proposed the Golomb codes, which is used in digital communication. And he has a paper on how mathematical modeling may lack in certain aspects. And he has listed down a complete set of don'ts of mathematical modeling. So I'm just going to show you a sample of the guidelines that he is offering. The first guideline he offers is that don't believe that the model is a reality. And to highlight this, he says that you will never strike oil if you try to drill a hole in a map. A map is a model of reality, but it is not the reality. Similarly, you can imagine a man with homemade vulture wings trying to fly like a bird and jumping off a cliff. You would obviously say that this person is not in his right mind, but we often do the same thing when we are working with mathematical models. We imagine the mathematical model to be the reality, which is not the case. So another guideline he offers is do not extrapolate beyond the region of fit. In regression, we are actually estimating a linear relationship, but we are estimating that from data which is only from a certain region. If we try to extrapolate this relationship to outside this region, this is actually problematic, because almost all processes that are linear in some portion of their operating region, they are non-linear in some other regions. So if we actually try to extrapolate the result to those non-linear regions, we would fail miserably, because our extrapolation would be way off mark. So an idea to illustrate this is an ice skater heading blithely towards the unfrozen part of a frozen lake. So this person is unaware of the fact that the lake is not homogeneous. It's not the same everywhere. It's not frozen everywhere. If it's frozen here, does not mean that it's going to be frozen everywhere. And like this man, the ice skater is going to be surprised. We may be surprised if we try to extrapolate beyond the region of fit. Another guideline is that we should not retain a discredited model, and we should not distort reality to fit our model. So to illustrate this, we shall use a story from Greek mythology in which a man named Procrustes had a bed which he asked his guests to use, but the problem here was that this bed was a single size bed, and he actually fitted his guest to these beds. So if the guest was a little smaller than the bed, he stretched the guest. In other cases, he would chop off the feet of the guest so that they may fit in the bed. So we may unfortunately be doing the same thing to our data if we are trying to make the data consistent with our theory somehow by even modifying it. The last guideline we'll be talking about is that we should not limit ourselves to a single model. And the catchphrase used for this by Ghulam is that we must legalize polygamy. But we'll be talking of the example of the blind man and the elephant. So we see that none of the individual models are actually catching the reality, but if we have all of them together, we get a better model of what the reality may be like. Let's also get some guidelines from a related field in which mathematical modeling is used. So a related field in which mathematical modeling is used much is finance, in which many predictions are made on the basis of very intricate, very involved mathematical models. So after the 2008 credit crunch, in which there was a huge problem in finance because of over-reliance on mathematical modeling, two of the top quantitative analysts in the finance industry, they actually got together and they created an oath. And they suggested that this be used as a guideline by all mathematical modelers in the field of finance. And they called this the modelers' Hippocratic Oath. And Hippocratic Oath is an oath that all medical professionals used to take before they actually started practicing. So the idea is, before you start to practice in finance the usage of mathematical models, you must read this. I will remember that I did not make the world, and it does not satisfy my equations. Though I will use models boldly to estimate value, I will not be overly impressed by mathematics. I will never sacrifice reality for elegance without explaining why I have done so. Nor will I give the people who use my model false comfort about its accuracy. Instead, I will make explicit its assumptions and oversights. I understand that my work may have enormous effects on society and the economy, many of them beyond my comprehension. And the two analysts are Emmanuel Derman and Paul Wilmot. I'll wrap up this discussion by another quote by Mandelbrot, a scientist who we would talk about a lot when we discuss fractals and self-similarity. He said that, unfortunately, the world has not been designed for the convenience of mathematicians. So mathematics does not always capture reality. And with this, I'd like to wrap up this lecture by giving you one concluding remark. And this is, while mathematical modeling is a very important tool and we must use it because it is so useful, we must always keep in mind that this is an approximation, and we must validate the results from mathematical models from intuition, judgment, and other whatever techniques that we have available. I'll see you next time, inshallah. Thank you.